All right. Well, welcome back. We've got a new class here, Communication and Navigation Systems. So happy to have you. Let me get this set up for you. How are we looking there? That's not too bad. All right. Probably can't see my insignia very clearly. All right. So the first part of this is going to be radio communication. 1917, what's that, 105 years ago? The First World War brought about an urgent need for communications. Voice communications from ground to air and from aircraft to aircraft were established. Okay, you can see the rudimentary radio equipment on a table outdoors as they're looking up in the sky, presumably at the aircraft. The pilot transmitting back to him. Early aircraft communication. Communication takes place by radio waves. Radio waves travel at different frequencies, and those frequencies are known as the electronic spectrum. So you'll see some terminology that you might know from earlier versions of television. Well, I suppose current versions: UHF, VHF. And if you're into more radio communication, certainly if you're amateur radio, high frequency, medium frequency, and low frequency are also used more for official purposes. There were some of the original frequencies being used. As radio technology developed, the speed of the radio wave or the frequency of the radio wave has gotten much faster for its current usages. Let's see here. Visible light, that's just a small portion. You can see the red, really small area there. That has its own distinct frequency and wavelength. And the same with electromagnetic waves. We can perceive some, but the rest of it is invisible. It's a broad range. At the outermost is gamma rays. Working inwards is X-rays, followed by ultraviolet. Those are the highest frequencies with the shortest wavelengths. The frequency is such that the wave is almost crunched together, so the length of the wave is nominal. Infrared radiation and radio waves occupy the lower frequencies of the spectrum. Radio waves such as FM and AM radio broadcasts are simply electromagnetic waves with a much lower frequency and longer wavelength than visible light. And those go together. A lower frequency means there's more peaks and valley space between a traveling wave. Another look at the electromagnetic spectrum. This time it's showing typical aircraft usages of communication and navigation. We'll see the high frequency communication takes place here, and you'll see that FM VHF com, or the communications, is right above pretty much broadcast. FM broadcast here is what, 88 to 108? And then right over that is the navigation VHF, and just over that is the communication VHF. So I mean, you can almost see it goes up FM broadcasts up to 108, and then the next 10 is navigation for VOR, and then after that it looks like about another 10, actually another 20, is for VHF comm, which is communication. That's most of the communication that takes place with an aircraft. Glide slope, DME, transponder. These are individual topics that we'll talk about. GPS, you're familiar with that. Radar altimeter, we talked about that a little bit in instruments. Doppler navigation, weather radar, that'll be new here. All right. It does say, notice that we use almost every band except for the very low frequency way here on the top and the extremely high frequency on the bottom. I mentioned what a radio wave might look like. It's a wave that has an up and down pattern. Maybe not exactly a pure sine wave. Pretty darn close to it. All radio waves consist of electric and magnetic energy fields that travel through the space. Two fields are located at right angles to each other and to the direction of wave travel. They are produced when a radio frequency electrical signal is sent down a conductor to an antenna, which transforms the signal into radio waves. Am I blocking this? I'm going to have to review this on different screens. Yeah. The radio system, and you may have already had a reading on this. Basically, it's showing you the various components of the radio system, and you can see there's a transmitter and a receiver, which are the equivalent of the computing or the smart portion of the system. Everything else is connectors. There's an antenna that transmits, and a receiver that has an antenna that receives the carrier wave. Certainly when you're transmitting, you need a microphone or some sort of input device. And when you receive, you need headsets or a speaker or some other form of output device. The basic operating frequency of a radio is called the carrier frequency because it carries the transmitted information from one place to another. The FCC requires all radio transmitters installed in aircraft to be registered and licensed if the flight operations are to be conducted outside of the United States. So if you're just going to have domestic travel, you don't need to have or display a radio license. But if you do fly to the Bahamas, the radio station license must be kept with the radio anytime a radio transmitter is installed and operated during international flights. And, somewhere along the line you will learn the acronym ARROW, which are like the 5 items that you should keep in the aircraft. And radio is one of the R's in ARROW. Like I believe registration would be the other R, an airworthiness certificate for the A and onward. You'll notice what I have here is the radio station license of Charles Lindbergh. I don't know if anybody noticed. So he had a radio in 1933 when his aircraft, the Spirit of St. Louis, set off for the Atlantic flight. The first powered flight over the Atlantic Ocean. Oral question: what are the basic components of a radio communication system? I would usually sit quiet and let you throw out some answers. Somebody might say the speakers. Another one might say the microphone. And then somebody who's into it might say something like transmitter or receiver, which are the main parts of it. The antennas, and I'm not sure, did we miss anything? Headphones, and all the wires that connect the two to the antennas. Microphone, transmitter, transmitting and receiving antennas, receiver and speaker or headphones. I think we got them all. And then some. When must the radio station license be displayed in an aircraft equipped with the two-way radio? When do you have to display the radio license? Well, remember, that was if you're going to do operations outside the U.S. So A looks like that would be the correct answer. It is. If you go through the FCC regulations, this is like the first one. This is the first one on the list. This is like 1-1-1. I may be exaggerating a little bit there, but it is right at the top of the list. I mean, it's a long list, too. It goes on for books. When would a U.S. resident not be required to hold an FCC restricted radio telephone operator permit to operate two-way aircraft VHF radio equipment? Now, we didn't talk about this at all. I apologize to you, but to go through what the requirements are to receive these various FCC licenses and what it permits you to do, this one I think we're just going to have to look at and kind of learn it while we're answering the question. All right, so when do you not need a permit? This doesn't say anything about a license. So A, when flying to or communicating with destinations outside the United States. B, when flying or communicating within the United States. Or C, when the radio equipment is operated in an aircraft certified for VFR flight only. Okay, when do you not need an operator permit, which isn't a big hurdle to get? That just tells you can talk into the radio. So that doesn't permit you to do maintenance on it or anything. We do have in avionics the next step, the general radio operator license, which grants technicians some expanded rights. So what is this? I would say probably C. This one, I don't know. Oh, it's B. So it's got a similar rule to the license. I see. So if you're outside the United States, it's the same as displaying the license that we showed, the Lindbergh license. The operator permit follows the same rules. Oh, sorry, it's been a while. All right, and then just pretty much to wrap up this section, we'll talk a little bit about radio principles so that they're not totally alien to you. Certainly the difference between AM and FM is a big item in radio communication, and the modulation, which is what this is. It's either amplitude modulated or frequency modulated. So this first one's going to talk about amplitude. And amplitude, it's kind of showing it here. It's a steady frequency, A, and that's the carrier wave. And apparently the amplitude modulated carrier wave is picked up by the receiver in this form because it is interposed with a variation wave, one that goes high and then low. You can see where 0 is. So let's say it goes up to 3 and then down to 2 and then up to 4, down to 2 again, up to 5. So you combine the two and you in effect get a carrier wave inside the amplitude modulated wave. It's transmitted in the form, so it's in effect the wave plus its mirror image. And the demodulator is able to extract the original wave, the original modulated wave from the carrier wave on the receiver end. Oh, man. It's definitely radio communication in a nutshell there. Frequency is very similar. Frequency is next. The modulating signal is standard, and the FM signal doesn't. It's either at +5 or -5. What is actually changing is in how fast it is being. If it had like little beeps or signals, kind of like Morse code. How fast is it going? So basically it speeds up and down. And it can be decoded in a manner similar to the AM waves. You know, if you wanted to get any of these licenses, we do provide an avionics program, which was originally designed for A&P technicians to come back, maybe take at night or while you're working, which is what I did. And you go into the detail much deeper, and you do pick up some of your FCC licenses. But we talk about some of these items in much more detail. But for our purposes, just be aware of the differences. You don't have to know that much about carrier waves for the A&P portion of the program. There's ground, sky, and space waves. You can kind of see the waves on the picture. The ground waves follow the contours of the Earth. Sky waves, it looks like it bounces off the sky, which we can see that's the ionosphere. And the last one here is space waves. It just keeps going out to space. Apparently, line of sight is another way of referring to space waves. There's a repeater here which can actually use space waves for this portion, and as long as it's going to be a straight wave, if you can clear terrain, you can use a line of sight with a repeater. So you can have a stronger signal, in effect, as opposed to very low frequency or medium frequency. Okay, speed it up. No, with space waves, you can have very high frequency or ultra high frequency. Yeah, so. All right, you can see the description of a repeater. It's a receiver and a transmitter unit. Picks up the space wave, amplifies it, and retransmits it on another frequency to the end receiver. And distances also. I sometimes will use the analogy of communicating with Orlando. And there would be a repeater at Yeehaw Junction. If your reference is South Florida. Because VHF radio signals are limited to line of sight, aircraft flying at higher altitudes are able to transmit and receive at greater distances. This figure illustrates the line of sight restriction characteristics that apply to VHF and other space wave transmissions. So be aware that there's probably not going to be a repeater on this mountain that you happen to be flying behind. So the terrain will block the VHF signals. And there's not going to be too much communication on, well, there's going to be no communication on very low frequency and very little on medium frequency. VOR stations, as well as the vast majority of aeronautical communications, do occur in the VHF band of frequencies. We saw that before, just over FM broadcast, the 10 steps for nav, and then the 20 steps for communication. What else are they showing us here? An aircraft at 1,000 feet above ground level over flat terrain may receive transmissions from 39 nautical miles. Okay. And if they were at 3,000 feet, it would be 69 nautical miles, so almost double. 174 if you're at 20,000 feet. I don't believe you're tested on this. Those items are given in this table over here. 39, 69, 174. But you are not tested on this. The basic components of the VHF communication system consist of a transceiver, all associated connections, and the antennas. The antennas used with VHF communications are Marconi 1/4 wave monopoles that use vertical polarization. A monopole, that's just one pole, that's an antenna that would be like sticking out from a walkie-talkie. And of course, since it goes straight in the air, it is vertically polarized. 1/4 wave, that's a one radio wave. It's like a sine wave going through space. You would, in effect, have an antenna that is the size of 90 degrees of that wave, 1/4 of the full 360-degree wave. There's usually a separate antenna for each VHF communication radio. Redundancy. And they are placed in various locations around the aircraft so that if your VHF signal is blanked by the wing or something else, you can still get communication maybe from a different angle. The airplane equipped with 2 transceivers usually has a microphone selector switch for the respective radios, so a second microphone is not required. Yeah, so you don't have to like drop one microphone and grab another one to talk in the second radio. You can just switch over. They're showing some other controls here. Squelch, frequency selector. You're used to that from automobiles. Adjusting the volume. I think we all know how to do that. The squelch is something that you don't have on most of your consumer radios. It basically, you're going to get a lot of background noise on a channel that's not being used, so you're able to turn it so that you don't hear the background noise anymore, but if somebody does chime in on that channel, you will hear them. That's adjusting the squelch. Question: what frequency range is used by most modern voice communication systems? As I told you, they're not going to test you deeply about this material. Very high frequency, VHF. I don't know if you want to say what specific frequency communications. That was Well, nav was 108 to 118, so communication started 118 to 137, was it? Holy cow. Darn close. And that's talking megahertz. Mega is a million hertz per minute. Is it per minute or per second? Holy cow, I can't believe. Pretty damn sure it's a minute. VHF radio signals are commonly used in A. Both VOR navigation and ATC communications. C. ATC communications, that's air traffic control. C. VOR navigation. And VOR has kind of become its own word. It originally stand for VHF, Omni Range. And we know that VHF radio signals are used for navigation, 108 to 118, and communications, 118 to 137, 136.975. So A. The simple answer is just A. A radio stack. This illustration shows a complete set of radios that might be found on a typical general aviation aircraft. The frequency transfer buttons can be seen on the VHF communication and navigation radios. Normally it'll say COM on one side and nav on the other. Yeah, you can see the nav. I can't quite see the COM. Oh, there it is, COMM. And there's little buttons that, well, these white buttons will switch what navigation frequencies you have in the active and the standby, and the COM arrow toggles will toggle you from what you're actually talking on now, 122, and what you're standing by to talk to somebody else on, 118.9. You have somebody on hold. I think they just said frequency transfer. Maybe you can transfer from the top radio to the bottom radio. Oh no, they are just talking about the transfer button, so that's what it is, not a toggle. The VHF communications and nav radios shown both active and standby frequencies. Yes, that's what they do see. What's the last one you ask? I'll let you answer that. It's not required. In the bottom part also. A little overlook of what most of the communication antennas look like. As you can see, by and large, they're either a traditional radio antenna, which looks like a wire, or even a bent wire or a canted wire, or basically wire built into a composite structure in effect, and is better streamlined for use on an aircraft. They call that blades, and the wire part whip. And I'm not sure about this one. This one might be an in-between. That looks more nautical, actually. A variety of radio telephone antennas are illustrated, including blade, whip, pole, and combination type. I would imagine pole is the little vertical one that we have it up here on the top right. Oh, that's it. All right. Well, I appreciate you joining me, and we'll wrap it up there. Okay. You have a good day. See you next time. Goodbye.